Chisel-based tensor decomposition.
Introduction. Thanks for the organizers for organizing this nice workshop and for giving you the opportunity to speak. So, yes, I designed this talk kind of really as a follow-up to next talk. So, from just now, and kind of, well, it should be many things to be followed. We can have few views on how to bring that out, but let's. Well, I've two kind of different parts, with both of them are basically. So recall we had this chiseling algorithm where somebody gets you a tensor which has low x rank with respect to some variety x, and you apply this slicing chiseling algorithm which computes some specification of your tensors with blocks, and the question is, or the hope is that and we put in some assumptions, these blocks are precisely your x rank decomposition that you are after. And we have these cold assumptions, COLD, that are sufficient for this to actually work. And somehow I want to talk about two distinct instances where if you try to understand these assumptions, it kind of leads to questions that I think are maybe interesting in their own rights, and or that are interesting in their own rights, and were luckily already solved, or mostly solved by other people. So one is a connect and the first instruction, the directness. The directness is the D in bold, and some kind of natural non-diffectivity type questions. And then the second one, if I have time, will be this L, this locality assumption, the L equal D, and the connection between geometric and theory. So let's start with the first one. So I'll be working with the following setup. So okay, so FDOV is for me just it will be either SDOV or HDOV. You can and X is a variety that is invariant under the group action GLV. So something that you can write down without morally, this is something you can write down or define without choosing coordinates. You can generalize this setup a little bit by change the group and things like that. Let's be concrete and fix with this. There's already plenty of examples that fall under this. So working decomposition, if you want to write your tensor as a sum of, if you think of tensors as polynomials, you want to write it as a sum of these powers, linear forms. Char decomposition, where now the elementary pieces are not powers of linear forms, but polynomials that factor. I mean, the systematic polynomial tensors for me, which is the same as multiplying linear forms. So the elementary pieces would be just polynomials that factor as opposed to linear forms, or something like W-state decompositions, where this comes from previous thoughts. And where you want to factor when your elementary pieces are things that look like this. These all fall within this in the setup, or something like the Grassmann decomposition. But the skew symmetric is the most natural one. The variety of skew symmetric tensors, some elementary. This precisely Grassmann. So this is the kind of setup. So yeah, so for applying this slicing chiseling algorithm, the first thing we're indeed going to do is going to reshape the tensor. That's going to be a very useful thing to do, and I'm going to do it in the following way. So I'll write D as 2E plus F, where F is either 1 or 2, depending on whether in the odd or the even case. And I'm going to reshape everything to this space. So now we're going to be working with tensors that are very big in two directions and small in the third direction. And so we have a tensor in this space that is of x rank R, and I'm going to assume that these TIs are random enough. And so we want to recover these TIs using this slicing algorithm from Excel. And so maybe I think the most critical assumption is this last one, this D, which this is the one that says that the rank is small enough. I mean, these other assumptions. I mean, C is not really an assumption, and O and L. Well, I'll say a bit more about L later, but you can often fix by just taking off slices. But this is kind of really the critical assumption. So when does this hold? Well, this was already been discussed in the previous talk. So you can define a number which is the dimension of U stated to S. And so for S in your variety random generic, so for a random, this will always be the same number. So if you want the multilinear rank of a generic point in X will be viewed in this space, will be kx, and so term that you don't care about. So this is going to define it with multilinear. So this is what this number is. And then, okay, so clear, a clear upper bound to have directness is this one. Because, well, this direct sum of tensors need to fit in the space over there. And so you cannot have this being a direct sum. This thing about these violated. So just to make this very concrete, so for the Grassmannian, if you take any point in there, generic in this case, then this will be taken to S is well, this following span over here, write it out, which is a vector space of dimension E choose E. So in this case, this is like our necessary condition for directness. This is, by the way, better than, so if you would try to do the Grassmannian without any reshaping, it will only work up to N choose D, and this bound is somehow is better. So you have hope to somehow do rank decompositions after reshaping, like beyond somehow, beyond the few could do without reshaping. And for child, it's very similar, and then on the bottom it is something. And experimentally, usually, like except for some examples that I'll mention in 2 slides, these necessary conditions are also sufficient. So the algorithm works as long as these things are not violated, but can we prove it? And this is like the first instance where well, someone has studied this question before. And what I know before, maybe we can just steal their method. Oh. Okay. I think I think this may be some more versions of the slides, but I think I can make this work. Yes. So okay. So the title of the slide is some. The rest of the slides will be correct. So this is back to the general static. So this is a method that Alexander Blumenhoff and Ansgar used in a different setting. So if you want to study this question, we're going to define this number AR over here, which is defined to be the dimension of this whole space. So if you take R tensor, then you look at in these corresponding spaces. You take R minus 1 of them and you intersect with the next one. The dimension of this is a number, it will also be the same number. So, and directness by definition holds even only if this number AR is equal to 0, because being in direct sum position is the same as that one of your spaces doesn't intersect the direct sum of the other ones. So the question is the question is somehow how long does this number stay 0? So you have a sequence, and so the other thing you can see directly is that this number say are from an increasing sequence. If you put more spaces, the dimension over here can only go up. And so we have a sequence of numbers like this, and the question of for which RP of directness is the same as how long does the sequence stay 0. The other thing you can immediately say about the sequence is that at some point, like this intersection, if you add more and more spaces over here, it will not keep becoming bigger. And so at some point, the sequence has to stabilize at Kx. And so I just kind of have the sequence in any case like this, where P somehow the last value will hit 0 and Q is the first index for which it's stabilized. Then there's 2 more observations you can make, and both of them use the fact that this variety is GLV invariant, and actually also that this is an irreducible, that this thing over here is an irreducible representation. It was either HDOP or HDOP or SDOP, so that's irreducible, that's fine. The first one is easy. The fact that like when you stabilize, you will stabilize, it will fill the attack space. Others would fill the state subspace, but this state subspace had to be invariant of your group action, and this was like this. And so this number Q over here needs to be at least dimension Q divided by Kx. You could immediately from this, because else you somehow cannot fill so quickly. And the second one, so this is kind of half part, so this is the main one of the main result of the state of local causality, is that the sequence in the middle over here, it can stabilize. You have to increase at every step. But then this implies that somehow this P minus Q cannot be too big, can be at most Kx. As you have the stabilization somewhere over here, which gives you a lower part, to this number, and then you get that the sufficient condition for directness, which is kind of the necessary condition from the previous slides, from 2 slides ago, this one here, minus a correction factor. So this, well, it's not quite there, but somehow minus this correction factor, we now have shown at least some sufficient condition for this assumption to hold. And so the other ones I think already mentioned. For Chow and Cosmo, we now have complete at least sufficient condition for which algorithm holds. Of course, we still, so let me just say, I want to just say this once more because this is like a very explicit problem, especially for the Grassmann case that you can state after just only knowing linear algebra. In this specific case, I'm kind of hoping one can say more. So maybe it's once more, there's no problem. So here is a natural question, one of the 50 question that is makes you ask. So you've given 3 numbers, N, E, and D, and you want the largest R, such that there exist, or we're going for generic D-dimensional subspaces in C to the N. These spaces, the corresponding each vectors of the R spaces you chose, are in direct superposition. As so by the previous slides, so now, I mean, I had E D equals to 2E plus 1 before, which you can ask this question in more generality for any N, E, and D. And the same argument from the previous slide goes through. So the optimal R lies somewhere in between kind of this obvious upper bounds and this lower bounds we have from Gromov causality. The upper bound is not always attained, and this is this one exceptional case. If N is somehow quite small, then R is equal to 1 because every 2 of these spaces will intersect. We're going to say explicitly in the intersection. But apart from that, so we tried some examples. We found no Kant. For the first Kant examples, I wasn't brave enough to state it as a conjecture, so I've made it as a question. If we're not in this bad case somehow, is it then true that basically when you have space to fit these things in here, do they actually fit, or are there some more kind of defective cases where these things for dimensions? So yes, we talked about this for a bit, but we don't know how to solve it. So I'm open for any ideas or suggestions. Okay, this was the first half of my talk, and now for something completely different. Well, so this is about this locality assumption, and I'm going to do the specific. I'm going to do this specific for I'm working with the observation of the slide, so I need to catch my breath a little bit here. So let's consider the following question. You take a generic tensor in the space C, A tensor C, B tensor C, C, so and You ask when does a random tensor like this admit a sparsifying blocking? So sparsifying blocking is one that can be detected by the chiseling algorithm. So in pictures, like you want blocks in the following way. So you want non-zero blocks in such a pattern that the non-zero blocks that it's possible to label things in such a way that the non-zero blocks are on the spaces where the integers are to zero. So for instance, this setting over here has a label half, a label half, and a label -1, and these things so to zero, so here so this is the most general kind of things that that chiseling algorithm can detect. So somehow on the one hand, you would think naively that like, and this is also true for big enough, quite enough tensors, that if you choose it, that's okay, should be. If you choose a random enough tensor, that it will not admit any specification. But on the other hand, for instance, in like some very unbalanced case, this is actually true that the generic tensor to change your phase is sparse, and so. And this is what I want to start with. So this is actually this very natural question is also the locality question for the subspace variety. So locality is basically in case you don't, I mean, you don't remember from the previous talk of locality says space. If you apply chiseling algorithm, it will not try to further chisel down every single block. Because that will somehow add small blocks. So this is a connection to this. This. And so by definition, locality holds if and only if for generic tensor. So I'll take it as a definition now. For generic tensor, if you have something in the kernel, then these three matrices x, y, and z, they each have only one eigenvalue. And so the connection with geometric invariant is basically going, remembering where our chisels came from in the first place and going backwards. So we have this natural group action on this space. So this is our notion from geometric invariant theory. This action is generically stable if for generic tensor the stabilizer is finite. So for the expert, this is I omitted here part of the definition that requires the orbits to be closed, but that it's automatic in this case. So this should be fine hopefully. Now we can put it after the talk. And this is equivalent to the map from the algebra action having trivial kernel, and this map was exactly of delta t. So this is somehow the quite natural geometric invariant t connection. And then there are well, two papers, and some the authors are in the audience right now, and that specifies stability of this group action and the version with more tensor factors as well, using clustering transforms, and we can. Okay, well, there is a little bit of proposal that I sweep under the rug over here, for basically if you have to actually use patients, so you know, can maybe say during the questions, but basically locality holds if and only if this group action is stable, and so use and then somehow combining this classification here, you can basically say when this locality holds, and this classification is just imported from these papers up here, but it's somehow just one attack from that this is something and something very explicit over here in secrets. It's something quite explicit. Yeah, kind of because that's what I wish to the last part, but I'll step over here. Any questions?
this kx that you mentioned, so is this related to this function that you're saying that you put it geometrically?
I mean, kx is what kx really is the the multilinear rank of a random point in your variety after reshaping. That's so somehow because chiseling. Because chiseling is somehow made to detect block decompositions, you only have any hope for this to find you only have hope for this to find excellent decompositions if a random tensor in X is actually a small block. Like if a random tensor is somehow has like maximum multilinear rank, then our approach will never work. And luckily for most varieties of interest that one can cook up, that we can cook up, it's actually true that a generic, Chow and Veronese are the most extreme, where like a generic any tensor in there has like multilinear rank 1, 1, 1. But even for like these other ones, for like things like Riemannian, a generic tensor has a low multilinear rank, and that is why the algorithm works, and it's this kx is somehow the number that encodes that. So that's the way I think about it, at least.
Unique result that we first see that this is like a point two, right?
Yeah.
There were some assumption on the simple values. You have seen the simple.
Oh, that's no. So
I saw that you considered opposite decomposition. So I think that's.
Yeah. So the main theorem of Kessel-Wilson, it doesn't really need. You can replace eigenspaces by generalized eigenspaces, and it goes through. If you want to use it in practice, at first you get some computational problems if you really want to compute Jordan normal forms numerically. That's a bad thing to do, but you can get around it by two factorizations. So, simple algebras are not really somehow. Although we haven't, we should really tag the W states in numerical experiments before I will say this with too much confidence. But for the best measures, I did not speak. It's a nice thing. Yes.
So you had some question about sums of exterior powers of
yes.
This
one.
Yeah. So do you know? Do you have an answer? But if you replace the exterior powers with symmetric powers?
No, so we have the same. Yeah. The one thing to say, if you replace I don't have an answer. If you replace the exterior powers with symmetric powers, it's not literally the natural question that Chow decomposition will lead you to. So there's like two slightly different questions one can ask about in the symmetric case. And I haven't answered to either of them. So yeah. But I've only talked about the one that's most naturally related to the Chow, which may be the most difficult of the two. So is there a reason to believe that that symmetric would be easier than skew symmetric in this case?
Yeah, because I think that related to polynomials vanishing from union of generic subspaces.
Yes, in that way. Yeah, that's.
There's no contractor to Edward that plays this game.
Sorry?
There's an old contractor to Edward that plays this game of replacing symmetric with the, and I think that the game is kind of different. It's not.
Okay, we can maybe talk later.
So thanks again to
here.